Hello. So, we're going to start this video with a question. So, how long do you think it would take to write out the sum of numbers, so writing 1 plus 2 plus 3, all of those numbers, 1 plus 2 plus 3, ... up to 1,000? The answer is probably a lot longer than you think. You probably think it would take a long time. Very long time. But it turns out that writing out gigantic sums like this is actually something that's not only useful, but actually necessary in calculus. And I realize saying this is probably making you think, oh boy, can't wait. But that's why we're actually doing this particular video, which strictly speaking doesn't really have anything to do with the calculus ideas, but in fact is sort of a notational video so that we know how to do some more condensed sum writing. So it's time that we introduce this new notation that mathematicians use that represent this sort of repetitive, repeating addition. And this is called sigma notation. So sigma notation, so named because we use the capital Greek sigma, which is this weird looking E thing. And sigma notation is a way of writing repeated sums. So a sort of important part about this, and often what's sort of the hardest part in practice, is that you need some way of describing the things that you're going to add together. So you need some sort of formula or some sort of algorithm that tells you which numbers you are trying to add when you're adding together a whole bunch of numbers. So the repetitive part, sort of capturing how it repeats, that's the key thing. But let's start by sort of looking at the form, just sort of the actual notational form, and then we're going to sort of fill in what all of the pieces mean to sort of see how this all works. So sigma notation has this sort of key format. So we have the sigma that it's named for. There's going to be an index letter. So this will be something like K or J or L or whatever. There's going to be a starting value for that letter, an ending value for that letter, and some sort of formula that typically but not always involves that index. And this is sort of the part that is hard to write sometimes, but is also sort of the key part, the part that captures how it is repeating. So if we look at an example, right, this K equals 1 to 1,000 of K. So again, the sigma, so it's sigma notation. This K part is the index. That's telling you what the letter is that is sort of the key part for the process of repeated addition. And this is telling me that, right, this equals 1 is telling me that it's starting at 1, going to 1,000, and the formula, such as it is K, right? So our index letter is K, starts at 1, ends at 1,000. The formula is simply K, okay? So the way we would read this, like if we were to read this in a, on a page, if we were to read this out loud, we would say the sum, that's what the sigma part is, from K equals 1, the bottom part, to 1,000, the top part, of, and then the formula, K, right? The sum from K equals 1 to 1,000 of K. All right, how does that work, right? So like I've described all of these pieces, but not how any of this actually functions to tell us addition. So the general process, and this is one of those things that's really weirdly hard to describe and yet very easy to see. So I'm going to do my best to describe it here, but we're going to do a whole bunch of examples so you can see how this works in practice, which will probably is where it's going to click. So we plug in the starting value of the index, right? That, again, that equals start. So we plug in that value into the formula everywhere where you see that index letter, right? So if the formula is something like K squared plus 1, and the index is K equals 1, you plug that in for K squared, right? Everywhere you see that letter. Then once you compute that, right, if it's K squared plus 1, you do 1 squared is 1 plus 1, right? So then you have 2, right? So you compute whatever it is. Then you increase the index by 1 and do that process again, but whatever you get as your next computation, you add to that first piece, okay? So you basically keep doing that process. You keep iterating this. Every time you keep increasing that index value by 1 and then adding it to whatever the running sum you have so far is until you reach that end value, right? So again, this end value up here, and that's the last one you add. Sort of importantly, we include both the beginning and the end, which this is probably never a thing you've bothered to think about, but in the English language at least, we actually don't do this naturally, right? If we say like how many numbers are between 2 and 5, you usually don't include both 2 and 5 in that process, but we do here. And this is something that's actually going to be sort of coming up and maybe a source of confusion when we sort of do this in practice in our calculus. So this is sort of a glance forward, something that'll come back up again. But to be clear, we do include both the start and the end. All right, so let's look at, again, the example that we have, the sum from k being 1 to 1,000 of k. So again, we start just by plugging in that first start value, right? We plug in 1 into our oh-so-complicated formula of k, everywhere we see k, right? Well, there's nothing there really to do, so we just plug in 1, we have 1. We have computed this thing, we write that down, we have 1. But then we increase the index by 1, so now k is 2. Plug that in, which is just 2, because right, it's still just k. And then we add that as a running sum. So here we had 1, we're now going to add 2, so we get 1 plus 2. Crazy stuff, I know. And we do it again, right? So we increase k by 1 again, so now it's 3, plug it in, compute that to be 3, now it's plus 3. So we keep doing this over and over and over and over and over and over, and we get up to, say, 999, right? So the dot, 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 right? We just keep iterating. We keep increasing by 1 and going. At k equals 999, we still have that 999, right? Because we plug it in and compute, we just get that value. But again, we do include the end value, so then we iterate again. We get up to 1,000. Add that to the running sum, we get plus 1,000. But now we stop because we've now plugged in that last value, right? So we've now gotten to 1,000, so we stop, okay? So this, on the left-hand side, is a very nice condensed way of writing out exactly that sum of 1 to 1,000 without having to use dot, 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 and without having to actually write all these things out, okay? So some important notes. So the index letter doesn't particularly matter. It should be a letter, but other than that, it's really kind of a free-for-all. That being said, by convention, sort of the ones we typically try to use are I, J, K, L, N, or M. We definitely want to try to stay away from letters that tend to represent other things, like X and Y are usually variables, so we don't want to use those. F and G are usually functions, so we don't really want to use those, right? E is usually the irrational constant. We don't really want to use those. So, like, technically speaking, it could be any letter, but try not to confuse people is basically the rule of thumb, so that's where we land on a lot of these. The index value, this is really important, has to always be an integer. So we don't want to have k starting at 1/2, for example, because we want it to be always a whole number. A way of thinking about this is that k doesn't necessarily represent sort of a number you're trying to compute with so much as the step you're on in completing this process, right? So when k equals like 1, we want it to be 1, the step, right? Not k equals pi, because then that doesn't really make sense. We're not on the pith step of the process. That being said, it can be an integer, meaning that it could be positive, negative, 0. Sometimes it sort of helps to start at a different value. So although most of the time we start our sum process at either 0 or 1, these are sort of the most common places to start, there is some good reason for making sort of the formula look nicer that we might start at a different value. But it's always an integer. This is key, right? So there's some little bit of flexibility in terms of, like, you could start at the -7th step in some sense, right? But it still needs to be an integer. There's no leeway about pi or 1/2 or something like that. All right. Typically, the formula that you have inside that sigma, typically this looks like some function of the index letter, because the idea here is that you're plugging in that index and sort of computing to get whatever number that you're trying to represent as that running sum, right? So in our example with the k going from 1 to 1,000, our formula was very straightforward. It was just k. But we could have other things there. Like if we wanted to add together only the even numbers, maybe we do something like 2 times k. That way we get 2 and then 4 and then 6, right? So you can have a formula, even very complicated formulas, but it typically looks like some formula of the index because that's how you're figuring out sort of the next number to add. Again, that being said, technically you don't need to have it there. You don't need the index letter to be sort of in there, and we'll see an example of that and what that means. Finally, the sigma notation represents a sum, and that means you can do things with it that you could normally do with sums, right? So for example, you can reorder sums, right? You could do like, instead of a plus b, you could do b plus a, right? It's commutative is what we say. It's also associative, right? You can regroup how you decide to add them. So you could like add different sort of sections at a time. The key thing to know, though, is that this is not true when the sum is infinite. If the sum goes to infinity, all bets are off. And I cannot stress that enough. Everything breaks to the point where like even rearranging the order can change the value, which is really weird to think about, that like if you change the order that you add stuff together, it is actually then possible to get a different answer if you're looking at infinity. The rule of thumb is whenever infinity is involved, everything breaks. Now, for the most part, we're not going to be doing much in the way of infinite sums, but they will show up in one particular section in this class. If you move forward in calculus, they will show up a lot. So at that point, it's sort of important to know this going in, that when infinity is involved, all bets are off, and you really want to be careful about what you're looking at, okay? All right, so as promised, let's look at some examples. Again, this is sort of difficult to describe, and this formula of k is not particularly enlightening. So we're going to go through a bunch of different sort of styles of examples and see how they work. All right, so this particular example here. So here we have our index k. It's starting at 0 and it's going to 5, and our formula is 2 times k. So to do this, right, we would plug in the first value. We plug in that 0 as k, and we compute. And then we would iterate, right, increase k by 1, plug in that, and compute, and so on and so on and so on until we get to 5. So if we do that, we will get something that looks like this, right, where I say compute, but I'm sort of leaving it out so that you can see how this is working. So to be clear, in your own work, you don't have to show like this particular step or anything. I'm doing it so that you can see how this process is working. But here, right, we have 2 times whatever k is. When a k is 0, I have 2 times 0. Then I increase k by 1, so I get 2 times 1, right? And I'm adding this as a running sum. Then I increase k again, so it goes from 1 to 2, so I add 2 times 2. Then I add, increase by 1, 2 times 3, 2 times 4, 2 times 5. Now I've hit the end value, so I stop. So this thing on the left is representing this running sum here, okay? And then I could simplify this. So if I actually do it out, right, 2 times 0 is 0, 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, 8, 10, all of that put together, you end up with 30. I know, deep math in a calculus class, right? But again, the important part is to see sort of how you get from this step to this step, okay? So another example, we could also do, as mentioned, negative values, right? It is commonly the case that you start at 0 or 1, but it certainly doesn't have to be the case. So here, we're starting with an index letter now of n. It starts at -3 and goes to -1, and our formula is n squared plus 1. So that means we're going to plug in -3 and get -3 squared plus 1, then add 1 to n, right? So -3 plus 1 would be -2, plug that in, do a running sum. So if we do this, here's what we get, right? So we plugged in -3 into our formula, so then we have -3 squared plus 1, right? Then we increase by 1, so that's -2 now, right? Again, to be clear, we're always increasing by 1, not increasing the magnitude, but going to the right. So -2 squared plus 1, -1 squared plus 1. Again, now that I've hit -1, the ending value, now I stop. So this thing on the left is the exact same thing as this thing on the right. And then once I have it written out, I can actually compute this, which gets me, right, -3 squared plus 1, that's, right, -3 squared plus 1 is your 10, -2 squared plus 1 is your 5, -1 squared plus 1 is 2. Add all those together, you get the 17, okay? So what about an example where we don't have the letter, right? So here, my iterating value, my index value is I. I'm going from 3 to 9, and my formula is just 2. But we do the same steps. So we plug in I equals 3 everywhere there's an I. Well, there is none, so we just get 2, right? I quote unquote plug in I equals 3, but there's nowhere to plug it in, so I just end up with that 2 value. But then I iterate, right? I increase that I value by 1, so I get I equals 4. I plug in that new value and do a running sum. Again, plugging in I equals 4 or 5 or 6, this doesn't actually change the value. So my running sum just ends up being this 2 added together a bunch of times. So in particular, I get this thing, where this first 2, right, is when I equals 3, but it doesn't change anything. Then I add when I equals 4, but again, that doesn't change anything. Then when I equals 5, 6, 7, 8, and 9, right? So I just am adding the same value together a bunch of times. Now, if you tried to do this quickly in your head, right, and this is the inclusive part I was talking about, if you tried to do this quickly in your head and you're like, all right, I go from I equals 3 to 9, and I'm adding 2 each time, in your head you might say, okay, well, 9 minus 3 is 6, 6 times 2 is 12, the answer is 12. Nope, it's 14. Because when you're doing that 9 minus 3 in your head, that's not what's actually happening. Because what's actually happening is you're including both the 3 and the 9, right? So it's really easy to make that sort of mental slip. So remember that you're including both. So if you're going to do something like that, like the 9 minus 3, you really want to go one more lower. So it would be 9 minus 2, which is 7, times 2 gives you that 14, okay? So again, this is sort of a weird quirk of how we talk about math versus writing math, but nonetheless, it's not too bad once you're aware of it. All right, how about a more complicated formula? So here we have what looks like basically a quadratic, right, of this index letter m. So here m is going from -1 to 3, m our index letter, and this is our formula. But we do the same thing, right? We plug in -1 for all of the m's and compute it, then add 1, so then we get up to 0, plug it in for all the m's, add together, and continue. So we get this beast of a thing, right? So we end up, if we look at it, this is where m was -1, right? So I plugged it in for both m's. This is where m was 0, so I plugged that in for both m's. Add another 1, so m is 1, plug it in, m is 2, m is 3, and then I can compute all this stuff. That gets me to a total, which is 10, okay? Last but not least, all the ones that we sort of looked at so far are some version of a polynomial, but there's no reason that needs to be the case either. We could put any sort of fair game function in here. So for example, we could also do logs or exponentials. In this case, we have an exponential. So here I'm starting at j is 11 and I'm going to 13. So if you, again, as that quick mental check, if I ask how many things am I adding together here, it would be easy to say 2, but the actual answer is 3, right? Because I have when j is 11, when j is 12, and when j is 13. So if I plug in the 11 up here, I'm going to get 2 to the 11 minus 10, so 2 to the 1 plus 1. Then I increase j by 1, so j is 12. Plug in, running sum, I'm going to get something that looks like this, right? So again, here is my j is 11 version, my increase by 1, so I get j is 12, increase by 1, j is 13, and I have this running sum, which gets me 3 plus 5 plus 9 is 17, okay? All right, so what do we do? So we've introduced this sigma notation, which is something that we'll need soon, sort of as we keep going through calculus, but is strictly speaking not actually a calculus thing. It's just a way of writing repeated addition. There's no limits involved, there's no derivatives, there's no antiderivatives, there's no crazy like calculus-y things happening here. But the idea here is that this notation allows us a nice condensed way of writing a whole lot of addition together. And it turns out that doing that is going to be eminently useful. Very soon, we're going to be sort of adding together a bunch of stuff. And so it's sort of helpful to have the sigma notation there to show us, or to sort of write that very succinctly. But a side effect of that is that we have this sort of algorithmically described form of the things we want to add together. Or in other words, we need some way of writing a formula that represents the values we're trying to add together. And so this is sort of one of the hurdles that we're going to have to go through in the near future. Okay? So that is that.